Hello guys, so this is another quick start for PyTorch where today we will show how to implement a simple neural network from scratch in PyTorch framework, and at the same time you will see the different terminologies that we normally use in deep learning for understanding of the network and how to deal with basic stuffs in deep neural networks. So we'll do and we'll go step by step, and it will be a quick start project, so you will be able to code a deep neural network completely from scratch in PyTorch after completing this tutorial basically. So the basic funda of PyTorch is nothing but it's similar to TensorFlow framework for deep neural network implementation. So all the low level codes and details that are required for coding any deep neural network are already coded for you in these platforms. Okay, and it is much more easier than to code neural networks from scratch, right? And then to have your own frameworks. Okay, so the first thing to work with data and data sets, let's say you have CSV files or images or audios, whatever, right? To work with those files inside PyTorch you require two model. Basically these are very primitive things. Okay, so the first one is you will require this data loader, and the second one is this data set. So this data set and data loader will enable your data loading part, and based on this you can do the ETL portion or the data pre-processing portion of your deep neural network implementation. And once your data is set and in a proper tensor format, you can simply implement your model using PyTorch, and then you can do the next steps, right? That means post modeling steps and all. So you can see that we are going to use this fashion MNIST dataset here. Okay, so you have already gone through the courses, I guess, on the TensorFlow sites. There also you have seen that we have implemented this same fashion MNIST problem using TensorFlow. So you are already familiar with this data set. Like we have 60,000 training and 10,000 testing data, and it's a grayscale image. So we'll only have black to white transition in terms of what coloring, instead of RGB color filters, and we have 10 classes. Okay, so this is the overall details of the data set. You can definitely take this notebook and work along with me from this description section of this description box. So what are the required modules will be requiring to import? So first you will be requiring torch for your TensorFlow library, for your deep neural network libraries. So within torch, as we are showing, this is a computer vision example, right? So we'll be requiring this torch vision, and from this torch vision we are going to import this datasets library, basically, that we have already talked about, right? Data sets and data loader, these two things will be required. And for some transformation of images, we will be requiring this lambda and two tensors. So we'll be describing all of this later. And for plotting all the images, right, we require this matplotlib for all these metrics and grid value sets and all. So you can see here two things we have imported. One thing dataset from torch.utils.data, and one is datasets from torch vision. Okay, so remember these two things for within this code, right? So now what we are going to use, we are going to use this datasets module. Within this datasets submodule, basically we are going to call this fashion MNIST method. So if you go to this datasets module, I have it open basically. So if you go here in this datasets module, you can see a lot of pre-built deep neural network datasets are already available, part of it. in it their root directory. So what it will do, it will help when you have when you are doing you know, let's say image classification. So you can quick start with all of this data and your custom made, let's say, neural network. So you can perform the performance, you can perform the network, and you can compare the performance of your model based on already pre-existing model, and based on that then you can decide, and you can, you know, train your own neural network on your company's data set, or for your private project or your personal projects and all, right? So yeah, once you apply this fashion MNIST method for downloading this fashion MNIST data, you will be requiring to give these 4 mandatory arguments. First one is the root, so where the data needs to be stored. So root will be your root directory, so we are mentioning here as data. Then second, this train flag, so if you make it as true, then it will download the training portion of the data. If you make it as false, then it will download the testing data. Then whether it is required to download or not, so if you don't make it true, then probably you already have the data downloaded in your local directory, so that's why it will skip the download. Okay, and the last one is transform. So this transform method will be implemented to features, that means your images as well as your labels. Okay, this thing you have to understand. So what happens normally, this fashion MNIST, right? So these are all images data, and it stores in the low hard drive or hard disk as images, right? But your PyTorch framework or your any neural network module, right, does not work with images, right? So you have to convert it into a format so that it is easily I mean, the neural network can easily work with the data, right? So for that we are just mentioning that, okay, transform it to a tensor format so that we can easily feed this images to our neural network, right? So for that we are using this toTensor method that we loaded or imported from this transforms submodule, right, or directory you can say. So if you run, so you can see we already have previously downloaded. So it first checks on this directory, this data directory, and it finds all the data is there, right, this fashion MNIST and all. So it skips the download and it runs as success. Okay, now the next one is so we have already downloaded the data, okay, and we have used this datasets basically module to perform this operation. So once that is done, what we are going to do, we are just going to iterate and visualize the dataset. So these are a simple dictionary that contains all the 10 mapping from numerical to categorical values, or basically string. So you can see your training data have all the labels as integer, so we have just converted them into their proper naming format. Okay, once that is done, this code is nothing but the figure size that you are mentioning, and for this we have used matplotlib. Then we are creating a 3x3 grid to plot 9 random images. So once that grid is completed, right, first thing what we are doing, we are selecting, we are using this rand integer. So in our previous QuickStart you have already gone through that rand int, right? This is a function implemented inside Torch that will give you a random integer, and we are passing the length of the training data, that means 60,000, and we are picking any one values, random integer values from 0 to 60,000 basically, with 60,000 will be the final limit, not including, and this dot item method will give us the numerical value, okay, that we can use as index in the next line. So in next line, as we have seen that we have already downloaded this training data, right? So this object is available with us. So within this training data, if you pass this index, that index will throw you the image and the label. Okay, this two things it will throw. And once we have the image and the label, what we are going to do, we are just creating one subplot, that means this section will get created, within that subplot we are passing this row and columns. So your row and column is 3 by 3, right? So 3 by 3 comma I means 3 by 3 comma 1. Okay, so in this portion it will create the it will plot the first image basically. Then you are writing the title, so your title is nothing but the labels. So from where you get the label, you get the label from this line. So once you get the label, it will print it as the title. Then you are just showing your images by using this squeeze method. So squeeze method, what it will do, it will reduce the unnecessary dimension. So let's say your images which are 28 cross 28, probably it has 1 cross 28 cross 28 kind of a shape. So when you do a normal plotting with x and y, it will throw error with the for the shape. So we are using this squeeze method to just squeezing those additional dimensions, and it will plot you the required objects. Okay, so if I run it now, it will perfectly run and it will show you all the random 9 objects. So I hope you have understood all the codes that's written here. So next thing is preparing your data for training with data loader. So you have seen the work of data sets, right? So data set works well with single images, right? This dot item thing, right? So single image or single item with this data sets API, you can definitely work with some iterator and you can see, right? But for machine learning, I mean particularly in deep learning, we are not going to deal with single examples. Rather we are going to deal with batches of data, yes, for learning, shuffling and training, right? So for this data loader API helps a lot. So you can read more about this data loader API from internet. I have also mentioned some of the required stuffs. So this data loader API requires the data, okay, so this data for training or testing. Then the batch size, so let's say currently we require a batch size of 64, and there is a shuffling. So for testing you can keep your shuffle equals to false. For training you can keep your shuffle equals to true. In this example I have kept both shuffle equals to true. So I mean normally for training you require shuffling, for testing why you require shuffling, right? It will do only inference. So that data loader you can get from utils.data. So once the data loader is imported, you just pass this to 3 parameters and your job is done. So this is how you don't have to write this codes customly. You get all of these features, right, along with PyTorch, and that is the beauty of PyTorch or TensorFlow while working with deep neural networks, right? So if you run this code, it will create a train data loader object and test data loader object inside your live memory, right? So now if you have to iterate through this data loader, what you have to do, for any iterator in Python, you use this iter function and you call the next function, right, on top of it. So once you will call, it will load the first example. Okay, so once your first example is loaded, then you can see this train features, test features, train levels and all that, right? So this train loader, what it will have, okay, so this train loader object has 64 objects or one batch, right, inside it, right? So your if you just run this line, right, feature batch shape, that means your train features dot size, what it will get, it will give you the size of the feature, which is nothing but your image size. So your image is 28 cross 28 that we have already seen in this data set example, right? And there is 64 is for your batch number. Okay, so this is how you have to understand the shape, right? And from where you are getting this train features and train levels, from this. So your train loader, once you are iterating over it, you will get train features and train levels, right? So the size of this feature will be your 64 batches of images with 1 times 60 or 24 28 cross 28. For any RGB, it will be probably 3 times 720 cross 720 or 1080 cross 1080, whatever. Okay, now for level will be nothing but one dimensional array, I guess. So your level will be 0 1 2 3 4 5 6 whatever, like that, right? So it is if you see, the size is as you have 64 images, so 64 levels for that in a tensor, right? So this torch dot size 64 means it's a tensor. Okay, so this two again, so you have this 128 as size, so you have to use this squeeze method to plot the images, right? The same thing again we are showing. So if you see, this is the feature batch shape, then another the level shape, and then you are getting the images here. Okay, and then you are just we are printing the level as level name that we have taken from here, right? Okay, so again, if you write copy this portion of code and run, then what it will happen, it will go to the next iterator, that means next example out of this 64 example, and it will plot and it will give you the value, and this is the last example, right, of this first batch. Okay, so this is how you use datasets and data loader API basically in PyTorch to deal with the input data basically. So with very small set of data, right, or probably data that will fit in your memory, you can directly use this set of codes to see your images and all. Okay, now next important or crucial point of any image classification and all model is to normalization. So why we require normalization? So that a reduction of the precision accuracy does not happen. Okay, so let's say you have one pixel of 17 and another pixel of 200 or 197, right? So this pixel of 200 will give more importance in feature selection than this pixel, right? So to avoid this kind of thing, we do a normalization between 0 to 1 or -1 to 1, so that what will happen, the prediction accuracy does not get reduced. Then due to this huge amount of uneven distribution of data, let's say you have you took a salary as an example, right, a numerical feature where your minimum salary can be 0 and maximum salary can vary to millions, right? So if you don't do a standard normalization there, what will happen, the model will get very much difficulty, okay, to understand that feature. Okay, so that's another point. And as I have already mentioned, this unfavorable distribution of feature data, right? So this for these reasons you need to do some normalization. And again, the transformation. So why transformation requires? So you receive input, let's say in a raw format, so you, before passing or feeding it into the machine learning or your deep learning model, you need to transform it to the required format. Okay, every model has a certain set of standards, so you have to abide the standards, and for that you will require some transformations that we will see in next, right? So again, from Torch Vision we are importing datasets, and as we have mentioned, 2 tensor and lambda, right? These two things now will be required in this code. So if you go in upper side, you will see we have already imported all of this, right? So yeah, once this set of code is done, now we are here. So let's say we are again importing this dataset as ds. Okay, so here what we are doing, we are doing a training equals to true, that means download the training dataset in this ds object, then transform and target transform. There are two additional parameters that we will discuss here, right? Okay, so transform is for your features, that means images in this example, and target transform is for your levels, that means your levels in this example, that means your outputs, okay, for supervised learning. So what it will do, this lambda function will create a one hot shot encoding. Okay, that means if you have let's say target of 1, right? So as you have a 10 example, it will create 0 1 then 0 then 0 blah 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 till 10th value, right? So in that manner, if you have 2 as level, okay, so it will create 0 0 then 1, something like that, right? So I think I have made some mistake. Yeah, so you have 2 and you, let's say you start with index of 0, then it is also fine, right? Okay, so this transformation is happening in this target transform, right? So this lambda function is doing that. So you have already understood what's a lambda function in Python, right? If you don't have that understanding, you can quickly search on internet what's the lambda function, and you can get that understanding. Okay, so this is what this function is doing basically. So first, this torch dot zeros and 10 with a data type float, it initializing tensor of 10 values, and everything is getting initialized as 0. Then we are using this scatter method, and this underscore means in place operation, in place scattering method we are performing, and we are replacing this 0 with this torch dot tensor dot y value, right? Okay, so which index maps the value, will be just replacing that index with value 1. Okay, so previously we will having 10 zeros, and then based upon this scatter method, let's say in the fifth index we have the corresponding value of y, then that fifth index got replaced with 1. Okay, so in that manner we are creating one hot encoding vector in place of a simpler scalar value, right? So we can also do the same using I guess softmax probably. Yeah, definitely we can do that. Okay, now next one is your components of neural network. So I hope everyone knows what's a neural network and blah blah stuffs, right? If you don't know, we'll have a separate tutorials for what is a neural network and how to understand different parts of activation, then your ReLU and all that functions in separate videos. So these are the some understanding. You can go through this notebook and understand if you have no understanding. Okay, so once this is done, you have to just select the device. Okay, so we have already seen in the previous quick start, right? So here our device is set to CPU. Okay, so for creation of neural network, you have to define one class, a Python class in PyTorch, right? So how we will be creating, you understand here first, right? Your images are 28 cross 28, that means you have 784 features or pixel that you need to fed into the neural network, right? So we are not considering here any CNN application, we are just considering a basic deep neural network, right? Okay, so once our input layer will have this 784 features, then our first linear module, it will take all of these features, right, and transform it into, let's say, 512 features. Okay, then we'll pass one activation. So neural network is all about activation and non-linearity, implementation of non-linearity into network, right? So in that manner we will be passing one ReLU activation. Then again we will create another module or another layer of hidden layers that will also have, let's say, 512 features, that means 512 nodes. Then again a ReLU activation, then again a third module of, let's say, 512 features, it will take as input from the previous layer, and it will output 10 10 new nodes basically, that means the output classes. Okay, so in a simpler word, softmax implementation, right? So this will be our simple neural network implementation. So we are defining this class of neural network, and inside this we are passing this nn dot module. So this nn dot module is the base of implementation of all the neural network related activities inside in your PyTorch framework. So we'll be utilizing that one. So once it is there, this nn basically stands for neural network. So you just call it, you just initiate the constructor. Okay, inside the constructor you call first initiate a flattened network, as it's a DNN network, right? Basically flattened kind of a structure and sequential structure. So once you initialize that, you call this nn dot sequential. So we have already seen all of this in our TensorFlow videos, right? Same method, tf dot sequential, right? So here it's a nn dot sequential, and we are passing the first layer, which will be our inputs, that means 28 cross 28 this will be your images, and 512 will be our first hidden layer neurons, then a ReLU activation, then 512 from the previous input we are again creating another hidden layer of 512 output. Then from this 512 layer again this is a ReLU activation, we are creating this output of 10 neurons basically, right. So this is our linear a very simple linear neural network, and we are using ReLU as an activation. So once that is created, remember always we will be calling this forward method on top of this neural network class to get the logits or the outputs. Okay, so what this forward method will contain, it contains x. X is nothing but what data you are feeding, right, basically. So your what this x will contain, so if you can see, this x is nothing but it's calling this flatten method. That means we have mentioned here, right, this flattening thing. So and we are passing this image, and then once this right, our input is flattened basically, that means you have this 784 number of inputs, then we are calling this linear ReLU stack, right. What is this linear ReLU stack? Is nothing but a simple neural network that we have defined here by using nn dot sequential and nn dot ReLU, right. So we will call this one and we will pass this x, which is nothing but our image. Okay. Okay, so once you will implement this neural network, then what you will get this 10 basically one tensor with 10 records or probability of each classes, right, as a what you will use to get as a softmax. Then you have to do one argmax to get the maximum out of all those 10 units, and that will be your corresponding predicted levels. So pretty much simple. Yeah, I hope everyone have understood this implementation of neural network. So yeah, let's move forward. Then you have to define the model. So it's pretty much straightforward. You have to initiate the class, and to initiate the class you have to also initiate it to the device, right. So always remember your PyTorch, in your PyTorch model basically all the parameters needs to be in one type of device, right, whether it's CPU, GPU, does not matter, but it cannot be like half in CPU, half in GPU. Okay. So once this model is in your device, then you can print the model. So let's just create the model first and then call the model. So once you have called the model, you can see this linear ReLU stack, which is your sequential model, have the first linear where your input feature has this 784 nodes, output feature has 512 nodes, and every node has every layer has bias enabled. Okay, if you does not if you don't want to enable bias for any nodes, you can also mention here, right. So this is your overall printing summary of your models, and then we'll be implementing a simple input and output to understand how it works. So let's say x is my input parameter, which is nothing but torch dot random initializer of 1 times 28 times 28, and within our device. So this is nothing but a random input parameter, and our logic to then will be our model, where we'll be passing this value, right. That means this one random image, let's say, okay, normalized random image. So once we'll pass that, we can print the logic to see all the probabilities it is throwing. So this is all the 10 probabilities that our model is figuring out. So once that is done, what we are doing, we are calling this softmax function with this logic function, and once we will get the prediction of the probability from all of this, that summation will be 1, and once that from there we will call or utilize this argmax function to fetch the highest probable level. Okay. So if I do another print of this, you will find all the probability of this values, right, that will sum to 1. So you can see from here, this is 0 index 1 2 3 4 5 6. So this one has the highest value across all of the 10 values. So index or level number 6, that means this random data that we have generated, right, it belongs to, according to the model, it belongs to the category 6. So if you go top into our dictionary, right, you will see 6 belongs to shirt. Okay, so the random generated image is nothing but a image of shirt according to our model. So okay, that's pretty much straightforward and pretty simple to understand how to implement and get prediction from a neural network in PyTorch. So once that is done, we'll understand how weights and biases, how you can calculate. So our model will have all of the details that it has learned from this implementation, right, or training, whatever you will say. Okay, so this model dot linear ReLU stack 0. Okay, this 0, that means your first layer will give you the weights of dot weight will give you the weights of the very first layer, and the biases you can also get from by implementing same method, right. So these are very low level details, probably you will never required when you are implementing end-to-end values only for debugging purpose and research purpose, right. But it's good to understand how things work inside your programming, right. Now next one, again in that manner, right, you can get the shapes. Okay, because it's all tensors, right. So you can do whatever low level operation that you prefer or you used to do with tensors, right, that we have already seen in QuickStart 1, right. So here you can see the, for the very first layer, the weight shape is 512 times 784. Okay, and for biases it will be a simple scalar value of 512, right, because you have 512 neurons there, right. And then again for model layers you can put the image size and all, right. Now next thing will be understanding this nn dot linear. So nn dot linear, I don't think anyone has any problem in understanding. It is nothing but your y equals to wx plus v, right. So your inputs are x, your weight is the parameter that your neural network or your machine deep learning network will try to learn from, let's say, gradient descent or any other learning implementation. So and bias is also a parameter that will adjust for to reduce overfitting and all, right. Okay, so that is the basic of your nn dot linear, and once you have this linear set ready, then you will just apply a non-linearity, which might be ReLU, softmax, tanh, does not matter. So this nn ReLU is nothing but an activation that introduces non-linearity. Okay, so this is the definition of ReLU. I hope everyone knows it. Okay, so your delta of ReLU is 1. Okay, so you can also print all of this. So what is the method that's we are sharing, right. So to get the details of ReLU of, let's say, any hidden layer, right. So this hidden one is your first hidden layer that we have already implemented here, right. This hidden one is your layer 1 dot flat image. Okay, so after doing flattening of image, if you pass that image to the first hidden layer, it will store all the details of your hidden layer, right, first hidden layer. So if you pass nn ReLU method, basically it's function, this same function on hidden one, so you can print hidden one before and after ReLU implementation. So every positive neuron it will activate. Okay, that means this feature is important, and every negative basically neuron, okay, it will bypass. So whatever 0 you can see, all are negative values. So in that way you will understand all the low level implementations of deep neural network in how in programming or how in coding actually it works, right. So this will helps build your intuition. When you are in coding field, you will not get distracted from the things that you have learned, right, because normally what you do, you write 3 or 4 lines of code for your deep neural network. So internally you need to understand what is happening, right. So this nn.relu will give you all the tensors, okay, before and after, you can definitely see. Okay, now next thing is your nn.sequential. So that means building your neural networks. Okay, so flatten layer 1 relu and linear that I have implemented to give you an understanding. I hope you already knows this sequential is nothing but your layers, I mean in a sequence, right? So your layer 1, layer 2, output layer, all the connection whatever you build as a model, right, in the top. If you see this model we have built, right, this one, yeah, so this one is your sequential layer. Yeah, you can see here, you can verify this, right? So this is the same as whatever we have seen in our TensorFlow tutorials, right? And the final one is your softmax, which we have printed in our logits. Okay, that has a value ranging from minus infinite to plus infinite. So softmax is nothing but you can read here everything. I hope everyone of you knows this, right? The softmax activation function, it used to calculate the probability of the output from the neural network, right? So we have 10 classes here, so it will calculate the probability of each classes. So it only use on the output layer of a neural network most probably, right? Softmax definitely we are going to use in the output layer. Okay, the results are scaled to values from 0 to 1, representing the model's predicted density for each class, and the dimension parameter indicates the dimension along with the result value must sum to 1, right, which we already know. So whatever, if there is 10 levels, the summation of probability of one like test case belongs to each one of the class must sum to 1, right? So the node with the highest probability, let's say our 7th node with the highest probability, we'll get that by using argmax method, and that will give us, okay, probably this image has much similarity with the node number 7, right? So that is the story of softmax. And then your model parameters. So your model parameters are nothing but your weights and biases. So the same thing, how you can print. Okay, so you have this model object in your system. So once you have that, it has a property called named parameters. Okay, named parameters or parameters that you have to use. So if you use that, then you can print out, okay, the parameter size, the name of the parameter, and the values as well, right? So what we are first printing, we are first printing the model, which is our linear ReLU stack. That means we have first one linear, then ReLU, then linear, then ReLU, and then output layer, and again a ReLU implementation, right? So here you can see all the parameter size of the very first, we have already seen that, right? So where we have already seen this one here, right? So we have already seen the parameter size for the first layer. So here you can see for all the layers, right, with this portion of code. So with this for loop, you can see all the parameters and their learned weights and biases and all, right? Now next thing is auto grade, which is a property of PyTorch, or basically Torch framework. So when training neural network, the most frequently used algorithm is backpropagation. We already know, right? So what happens in backpropagation? Parameters are adjusted according to the gradient of the loss function with respect to the given parameter. Okay, that means your d of j divided by dw and d of j divided by db, right? These two things are main while we're implementing this gradient descent of the loss function, right? So the loss function calculates the difference between the expected output and actual output, right? So what this loss function will calculate? Y minus y probability, right? These two. The goal is to make this differentiation to 0. That means optimize this equation, and in this process it will go back and forth. This back thing is called your back propagation, right? Okay, this back and forward process of retaining the model over time to reduce the loss to 0 is what your gradient descent model, right? So PyTorch has a built-in differentiation engine called torch.autograde. It supports automatic computation of gradient for any computational graph. Okay, so this is a built-in PyTorch. So how you can example, or how you can withstand or witness that. Let's say you have a simple tensor, x as an input, y is your expected output. Let's say this wb is your w is your weights, b is your bias, and z is your prediction. So your z is nothing but a matrix multiplication between x and w plus the bias term. So this z you will get. Now you create a binary cross entropy with logit. So you create a functional binary cross entropy with logit for categorical variables. So once you have this loss function, okay, you are ready with this loss function, you can get create, basically it will fire your autograd here, okay, torch dot autograd, and it will automatically calculate the basically differentiation, okay, and the gradient basically. So what we are printing, we are printing loss, we are printing x, y, w, b, z, whatever variables here. You can see this is x is nothing but 5 ones, y the prediction is nothing but 3 zeros, that means 3 classes, and your z is here minus 0.0 whatever, minus 1.269, right? So there is a difference. So this loss, so PyTorch calculates it automatically. So you can see the loss function here, right? Okay, so your loss function will be one scalar value, I guess. So this 2.6 something is your loss function, right? So how you are getting all of this from this your computational graph, right, or gradient descent algorithm, okay. And how we are getting this scalar function? By utilization of item, I guess, right? Somewhere they have must implemented yeah, this loss dot item, right? This loss dot item will provide you one scalar function, otherwise you will get this also as a tensor. So somewhere, so you can see this gradient function, it is already inbuilt in PyTorch, right? So this is what we are talking about, right? So when you are applying a loss function, it triggers the gradient descent algorithm, and this is the function that got generated, okay. Now tensors, functions, and computational graph. So if you have any difficulty, okay, so you can understand this thing better in this portion of blocks. That will, I guess, help you understand this concept more clearly or concisely. So in the network, basically w and b are the parameters, right, that we have already mentioned, and which we need to optimize. Therefore we need to be able to compute the gradient of loss function with respect to those variables, right? You have understood this one, right? So you have w and b, which is first initialized at, let's say, 0.001, 0.1234, whatever value, right? This initial values we have to with respect to the loss function that it will calculate on the forward pass, we have to apply one gradient descent algorithm, so that this differentiation between, let's say, 0 minus 5, which is minus 0.5, can be minimized, okay. So to do that, we set the requires grad property of those tensors, okay. So for this w and b values, we of these tensors, we have to set the requires grad equals to true, right? That means it will teach them that, okay, this w and b needs back propagation and it needs further computation, right? So you can set this when you are creating the tensor, x dot requires grade in place true, okay. So for any in memory computation or in place operation, right, you use this underscore, right, that we have already discussed on the QuickStart 1 of PyTorch basically. So a function that we apply to tensor to construct this computational graph is an object of the class function, okay. So I hope you have already gone through basic of what is a function in your Python classes. So this object knows how to compute the function in the forward direction, and also how to compute its derivative during back propagation step. A reference to the backward propagation function is stored in the grad function property of the tensor. So what are the tensors that requires back propagation, or that requires optimization? Basically it's w and b, that means also z, right? Z is the combination of all this, right? So if you apply this z dot grad underscore function, right, what it will do, it will give you the reference, right. If you see, it will give you the reference of this back propagation step, so you can cross verify that one here, right. And also you can apply that to the loss function, so you can see this add backward 0 object at blah blah some memory location is nothing but is the reference of your backward propagation step. Okay, so computing gradient is nothing but whatever we have discussed, the computation of deltas. So what we are trying to optimize, we are trying to optimize the value of w, that means your weight parameter and your bias parameter in term of losses. So whatever loss function, that is the very basic of gradient descent algorithm, right. So this grad property of these parameters will give you all the gradient values. Okay, that also you can see. And then again for forward pass, right, we does not requires let's say when we have to do in the inferential stage, right, for all the inferential cases we don't need a back propagation, right. We just need to need the computation to kick off, and we just need the prediction. Okay, so in that case also for those tensors we can disable this gradation, right, sorry, gradient descent by disabling this to false. Okay, so to do that same thing, z dot requires grad equals to we have to make it as false. Okay, so this no grad, basically this no grad method, what it will do, it will disable the requirement for your whether you requires gradient descent or you requires gradient descent or not. Okay, okay, now next thing will be you can achieve the same with this detach method. So if you apply this detach method as well, you can again disable this gradient tracking. Okay, that is not required when you are in inference. Okay, that will help. There are some things which are known, right. If you disable, it will froze the parameters and also speed up the computation, right, whatever it is doing, right. And you can also learn from this link more about this computational graphs and all. Okay, the next thing will be optimization. So for optimization, whatever two things will be required. First one is your loss function, second one is your optimizer, whatever you are going to add a grade, add a boost and all that optimizes RMS prop, right. So those things will be required. And in deep learning, the most important thing that from a tuning perspective is your hyperparameters. So here also there are hyperparameters which are your learning rate, that will decide whether how quickly or how slowly your gradient descent will converge. Then you will have your batch size, the use of batch size we have already seen in data loaders, right. And number of epochs that we'll see in the model training time. Okay, for how many epochs we have to train. So a normal correlation is the more epochs you will train a neural network, the better it will perform, right. And it also prone to overfitting with the number of epochs. Okay, so these are simple initialization process. So you have to initialize, and then there are two loops while you run one epochs. The epochs will contain one training loop and one validation or testing loop, right. So what happens in your training loop, iterate over the training data set and try to converge to optimal parameter. What happens in validation loop, iterate over the test data to check if model performance is improving or not. Okay, and for measuring all of this, you requires what, you requires loss function, right. So commonly use MSE for regression task. For classes you use negative log likelihood or cross entropy loss to combines with your NNL loss and your log softmax. Okay, so these are the things we have already dealt and discussed all of this in basic format in our deep neural network classes, right. If you haven't watched, please do watch. Now first thing what we have implemented here, you can see we initialize the loss function which we are using this cross entropy loss. Okay, once this is initialized, and then we pass the optimizer, and in optimizer what we are passing, let's say we are using this SGD optimizer here, right, stochastic gradient descent. and within this optimization process we are passing the learning rate. I think we have set as 0.001, and we are passing all the model parameters, right? So you are understanding, right? We are what we are doing here, gradient descent algorithm, right? So what is the first process of any optimization? Two things for this deep neural network, right? Two basic things is required. One is your optimizers, which are your Adam RMS prop, okay, and second one is your loss function, okay. Now inside the training loop, optimization happens in 3 steps, okay. So how optimization happens, that we'll see now. So your optimizer dot zero grad, right, to reset the gradients of model parameters. Gradients by default add up. To prevent double counting, we explicitly zero them at each iteration, then back propagate the predicted loss with a call to loss backwards. PyTorch deposits the gradient of loss with respect to each parameter. Once we have our gradient, we call optimizer dot step to adjust the parameters by the gradient collected in the backward pass. Pretty simple to understand. This is the very basic step that we have already gone through previously in what is the back propagation and how optimization happens inside any neural network, right? Same thing we are implementing, right? Let's say for batches, so whatever batch size you have given, for that batch you have the training and testing examples, right, inside your data loader. So we have already dealt with data loader previously, right, and we have seen what are the outputs it provides, right? It provides feature list, level list, and batch size, right? You remember 3 times 28 times 28 times 64 was the shape of the data loader, first data loader example, right? So there what your x and y's are nothing but 3, 28, 28, and whatever y was 64, right? And your batch is nothing but the first 64, right? Now your prediction will be your model dot x will give you the logits. So once you have the logits with you, what you do, you calculate the loss function, okay. So let's say you have a loss function with you, so we are passing a loss function, right? For our use case here we initialize this loss function as cross entropy losses, right? So within this loss function you will pass y and your prediction to get the difference. So once you have once you computed the loss function, then you trigger the back propagation, right? So how you trigger the back propagation? You first call optimizer dot zero grade, right? So your optimizer is nothing but your SGD, stochastic gradient descent, right, which takes your learning rate and your model parameters. So they have your model parameters and they have this hyperparameter called learning rate. So you are calling this optimizer with this zero grad method, right? And why we are calling? To reset the gradients of model parameters, right? First it will reset the gradient, then gradient by default add up to prevent double counting, okay, and after each iteration we explicitly set them to 0, okay. Then we call the loss function in backward direction, okay, loss dot backward. So backward means it triggers your back propagation basically. So back propagate the prediction loss with a call to loss dot backwards. Your PyTorch deposits the gradients of loss with respect to each parameter, okay. So it will adjust in backward side the way it happens, and then we move forward, right? Then again your optimizer dot step, okay. Once we have our gradients, we call optimizer dot step to adjust the parameters by gradient collected in the backward pass, okay. Again we are calling the optimizer, right? So then you have some batch. If your batch is 0, these are pretty much straightforward, how many times you have to do or perform. So this is your training loop. So once your training is done, right, let's say you have gotten your targeted loss, or there is another thing is accuracy, right? If your accuracy is greater than this, or your loss is lesser than this, blah blah stuff, right? Based on that what criteria you will stop your training. And then in your testing is very straightforward, right? You will get the accuracy, you will get the average loss, right? So testing, there is no such concept of forward propagation, backward propagation, right? It's only prediction and then get your class, right? And based on that, okay, calculate this. If it's a classification, you get the accuracy, okay. And once all of this is done, okay, you can say that okay, your model is have done one complete learning. Okay, so when you called model.fit in TensorFlow, right, or let's say in scikit-learn, these steps internally it performs all that fit method. Okay, so once that is done, you can see all this epoch. In first epoch, what are the losses? In second epoch, what are the losses? And you can see, okay, this is how many based on the batches. You can see in third epoch, so we have given a 10 epoch, so you can see all the results. What are the performance of test data set, what are the performance of training data set. So you can see after every epoch our test error is improving basically, so our accuracy is improving in that manner. So finally we achieve around 60, more than 60% of accuracy, right? So this is to give you a high level basically understanding of how model dot fit works, I mean model dot fit in case of TensorFlow or scikit-learn, right? Basically these are the low level implementation of your gradient descent algorithm and backward propagation for neural network. So once all of this is done, then you can save your model with state directory. This method state underscore dict for directory for short, and you pass the model name and root. So we have used data as the root of this project, right, where our data got downloaded. Then we can simply load the model in model.pth format. So if I open this, I will have one model.pth there, right? And then you can convert these models. You can load this model anytime and you can convert it into a platform friendly version, let's say on ONNX, that means your open neural network exchange format. So same thing, you load the model, you first initiate this eval method for evaluation method, okay, for loading. And once that is done, you import open neural network exchange, and then you pass this torch dot onnx dot export method, and you pass the model, you pass the input image, you pass the onnx model, and this image is just for testing purpose for your shape, right? As I have already always in any deep learning method or deep learning class, I always mentioned that if you get any error, mostly it will be your shape error, right, that you have to, because there is nothing else inside the method. If you have right shapes, it will perform whatever it is intended to, and it will give you provided output. Okay, so this is the overall thing. I guess I mean that's it for today. You have understood all the basic implementation, and if you want to see all of this later code, right, it's the same thing here. We have only applied it on top of the fashion MNIST data, so you can see all the same implementation and all the records and outputs. So with 10 epochs here, it is providing probably 71% of accuracy. Then say same thing, right, saving the model, then again loading the model. Then once your model is loaded, yeah, your evaluation step, right, okay, model evaluation. So your actual versus predicted. So a pretty simple and straightforward approach of how to implement let's say a deep neural network by utilizing PyTorch framework we have learned in this tutorial. And if you have gone through this tutorial, you now have a clear understanding about very low level implementations of a neural network, how neural network works with image data. So image data is not important because you are applying this flatten thing, right? So this flatten already makes your matrix shape images as series of features. Okay, so nothing CNN we have implemented. So I will see you guys in the next set of tutorials where we will be teaching much newer concepts or some recent concepts about machine learning, deep learning, and data science related concepts. So for understanding and learning, stay tuned and please subscribe.